Hello everyone. In this lecture, I want to continue the normal stress topic by talking about the general equation for normal stress. So in the previous lecture, what we talked about, we were able to calculate the normal stress due to a bending moment only. So before going through the next topic, or the continue of the normal stress, I want in this example, which is the last thing I did in the lecture 13, I want to draw the bending strain for this beam. So basically what I want to do, I will also draw a line here, and this line where I will draw the normal strain on, or the bending strain on. And the reason why I drew the vertical line, because for that moment, the y is changing. So since y is changing, that's why I draw this line. So along this line, along y equal certain distances, I will have a normal strain at this line where I will go right or left. Okay? So basically, I will also calculate the strain at 2 points, at point A and at point B. Okay? So at point A, if you remember the equation from the strain, we concluded that y is equal y over rho, which is the radius of curvature. And then rho here is equal to EI over M. Okay? Of course, MX and IX. And then I will move this M up here. Then I will end up with MX y over EIX. This is the equation for the strain. And another way, if you want to derive this equation, if you remember the normal strain from Hooke's law is equal to stress over modulus of elasticity, right? And since we have a bending strain, the bending stress here is my over I, right? And then I do have the E here, so my mx ix, so mxy over iex, which is the same equation what you see here. Okay? So I will calculate the E strain at A. So the moment here, I do have 11.6. I'll multiply by 1,000 square because I want to convert the kilonewton to Newton, and then meter to millimeter. And Y is distance from the centroid to point A, which is 120 millimeters. Okay? Over E. So E in this question was not given, but for wood, the E for wood is 11 gigapascal, and gigapascal is kilonewton millimeter square. So I'll put 11 down, multiply by 1,000 to convert the gigapascal to megapascal, which is kilonewton, which is Newton now over millimeter square, and then Ix, which is 240 cube over 12. Now this equation, I will get 0.003078. Okay? And at point A here, since due to bending moment, it's pointing up, so it's negative, negative, and then positive, positive. As you know, the bending moment indicates the compression side, right? So if we draw the bending moment up, that means the upper side of the beam is in compression and lower side of the beam is tension. That's why at the middle here, we draw the cross section with the moment pointing up, and the arrow here indicates the compression. So if I put an arrow here up, that means the upper side is in compression, the lower side is in tension, and what divides the tension and compression is the neutral axis. That's why the stress at the top here was negative, the stress at the bottom is positive, and since I do have a negative stress, then I will have a negative strain. So I will go here, negative 0.00078, okay? And at the bottom, it's gonna be same thing. So I don't have to calculate the strain at B, which is here, because I do have the same equation, but the difference will be the sign. So negative here and positive and 0.0078. And that's what we call the bending strain. Okay? So now let's move to the next part of the lecture, which is the general equation or general formula for normal stress. But let me start with reminding you with some things that we covered before. So if I do have a cross section like this, and I had an internal axial force of N, and this internal axial force was causing tension to that cross section. So if I'm causing tension to the cross section or compression, that means that it's a normal stress, not shear stress. Because again, normal stress is when the cross section is feeling tension or compression. Okay? So due to this N, before we agreed that if I want to calculate the stress, so the normal stress here was equal to normal over area. And then I had plus or minus here, which depends whether the N was tension, so positive or negative, if N was in compression. So in that case, N was pulling the member, so I will put positive. Okay? So that was the case if I did have a normal, internal normal force of tension. But what if, which is what I covered in the first part of lecture 13, if I do have a moment, internal moment, mx, which is moment around x here. So if I have a moment around x, that means that the upper side of the beam there is compression, and lower side of the beam is in tension. Because if I apply moment like this, look at my hand, my lower part of my hand is getting pulled, and the upper part of my hand is getting pushed. That's why the cross section itself feels normal stress. So when we had that normal stress, so the normal stress equation now was equal to mx y over ix. Because this is the moment around x, so what is going to resist the bending, or the property of area that's going to resist the moment about x, was the ix, which is the moment of inertia about x-axis, which is the resistance to bending around x-axis. And y here, with mx, you're going to take the y distance. So y, we're going to calculate it from the centroid. So from the centroid, the my over I, this y is the vertical distance from the centroid. And the reason why the y is vertical, not horizontal, because the distribution of the stresses is when I apply the moment like this, the upper side is in compression, and the compression decreases until it reaches the neutral axis where it's 0, and then the moment goes to tension. So this distribution is vertical. That's why I do have a y, which is the distance vertical. And it does make sense, because that's what the equation tells me. At a vertical distance y, I do have a stress, which might be positive, might be negative, it depends. So the stress distribution is linear. Okay? So it's going to be either like this, for example, or like this. With linear, I mean there is no drops. Let me put positive. There is no drops. It's going to be straight line all the way. Okay? So that's in case if I do have mx. What if I do have an my, which is moment around y-axis now, which is, if I have this beam, when I apply mx, which is moment around, about x, this beam going to bend around x-axis. But when I bend it around y, which is, for example, that bending, if I apply moment that way, so this side, if you look in here, this side is in compression, this side is in tension, which is what is shown here. So if I apply moment here, so let your fingers follow the moment. So this side is in compression, and this side is going to be in tension, because this is being pulled and this is being pushed. That's why I will be interested in, now not y, it's going to be x. And x, again, measured from the centroid. Okay? So the stress here is going to be my x over iy. And again, iy, because this is the property of area of resisting the bending in the y direction, or around y. So now what if I gave you a cross-section with internal axial force N, and with a bending moment, internal bending moment mx, which is moment about x, and then m around y. So you have three forces here: normal, bending moment about x, bending moment about y. So the normal stress will be a combination of all three of them, and the combination will be normal stress is equal plus or minus n over area plus or minus mx over ix times y plus or minus my x over iy. Okay? And this is the general normal stress formula or equation. And plus or minus here, I'm going to teach you a method now to figure out this plus or minus. Okay? Before doing so, I want to go through a difference between eccentric load and axial load. So if I do have centric or axial load, what does that mean? That means that that column has a force or axial force that is on its centroid, that is applied on the core of the column, at its centroid of the column, or at its longitudinal axis of the column. And this is what we deal with. But in case you have something like eccentric load, where the load is not applied at the centroid of the column or along the longitudinal axis of the column, it is shifted by eccentricity E, which is the distance. What should we do in that case? And here's how it looks like in 3D. We don't deal with eccentric load. Instead, I want to move the load to the centroid of the column here. But here's the problem. When you move a load from one location to another, you don't only move the load. We move the load with a bending moment. In different words, if I want to represent this eccentricity, if I want to erase this load and just put it here, I want to take the effect of the moving of the load. So the moving here is the bending moment. Let me explain it in another way. If I do have this large number of papers here, and I just put it here. So I'm holding this paper at the longitudinal axis of my body, or like at the core of my body. So my body here feels the P, or the weight of the paper. But if I put the paper that way, away from myself, look at my body is bending that way. My core still feels the weight of the paper. In addition to this, the bending moment, which is the weight of the paper multiply that distance to my core. So this bending moment is what we're going to consider here. So we don't deal with eccentric load. Instead, when you see an eccentric load, you take the effect of eccentric load by moving the load to the middle in addition to the bending moment. So I'm going to put this bending moment, which is equal to P times E, and that's the bending moment. And the reason why I made it clockwise, because here this load is going to apply a bending moment around this point in the clockwise direction, as if this load wants to bend the column that way. That's why it's clockwise. If you look at here, this load around that point, which is around the center, is going to want to bend it clockwise. That's why I put the bending moment that way. Okay? So let's now solve an example. Or before solving the example, I do have another example for eccentricity. So if I do have a column like this with a cantilever, which is this part, we call it cantilever or corbel, and I do have a load of P here. Okay? And if we want to take the effect of this load, we want to move this load here along with the eccentricity. But here is a common mistake. So the common mistake is you multiply by this distance, which is to the edge of the column. No, the edge of the column doesn't support the weight of this load. Instead, you want to move the load to the center. Same as this paper example. In this paper example, the edge of my body, the skin, doesn't hold the weight. Instead, the core of my body, which is like the center. So when I multiply this load by a distance, I make sure that I want to multiply the distance to the center of the column, or like to the centroid, the longitudinal axis of the column, not to the edge. To the edge is wrong. To the center of the column. And here is the bending moment if I name this E, if this is E, and this is, for example, A, this distance is A, then the bending moment is equal to P times A. Okay? Let's now solve an example, which is same example that we did in the, like, at the first part of the lecture. But now what I did add, I added a 20 kilonewton here, which is an axial load. If I want to draw the axial force diagram for this beam, what I will do is I will have 20 kilonewton here. Okay? And the bending moment, we drew it before, so it's gonna be 11.6 kilonewton meter. Okay? So now, what I'll be interested in now is the cross section where I do have the maximum bending moment, which will be in the middle. So in the middle here, I do have a bending moment of 11.6, and I do have a normal force of internal normal force of 20 kilonewton. So if I want to take the section here, this cross section, and I want to draw it, so this is the cross section. Okay? And to represent this bending moment, so we drew the bending moment up. So the bending moment up indicates the compression side. That's why if I want to translate this in 2D, I will draw a line here with an arrow looking up, and the arrow looking up tells me the compression side is up. So I will say now m of x, or m around x, is equal to 11.6, and then I do have an axial normal force tension, and it's applied in the middle at the centroid. So I want to make a line here which represents the centroid in the middle. So centroid, or center of area. And I will point toward the centroid here, and I will write n is equal to 20 kilonewton. So I do have a cross section where mx is moment around x. This is x, for example. This is x-axis. And at the same time, it's centroid. I do have a moment, and then I do have a normal force of tension equal to 20 kilonewton. So I drew now the bending moment up, and let me assume at the beginning that the neutral axis coincides with the centroid. For sure it doesn't. So as we explained at the beginning of the lecture, that the neutral axis align on the centroid or coincide with the centroid only when the section only has bending moment. But when I have bending moment and normal force, which is what we're going to show here, the neutral axis is going to be shifted. But let's at the beginning just assume it's in the middle, and we're gonna change that in a moment. So if I assume that the neutral axis is the middle, neutral axis, the definition for it is where the stress is equal to 0, or where the tension switches to compression, or compression switches to tension. That's the point of, or like that's the axis where the tension and compression change. So due to the bending moment, I'm drawing here in blue that the upper side is in compression due to the bending moment, and the lower side is in tension, right? Because the bending moment, if it points up, tell me the upper side of the beam feels compression until the neutral axis, then up below which I do have a tension. That's due to the bending moment. And then due to the axial force of 20 kilonewton in tension, I'm drawing it in black, and I want you to symbol that. So I want you to draw the bending moment in a color that's different than the normal, because the signs here are going to be different. So due to normal, I'm putting positive here. All the quadrants going to feel positive. All the beam going to feel positive due to the 20. So on the upper side, I have a tension effect due to normal and compression effect due to the moment. The bottom side feels totally tension due to both of them. Okay, now I want to find where the neutral axis is. So I want to say neutral axis, which is NA, location. By definition, the neutral axis is where the stress is equal to 0. And when I have a moment now, a normal, the stress equation gonna be n over area, and then mxy over I. But I need to put the signs at the beginning. So I don't want you to put signs inside the equation. I mean, like in n over a or mxy over I. I want you only put the signs here. This is where you put the sign, which is positive or negative, positive or negative. And how are you gonna see this? From the graph that we just drew, which is with the help of this. So here is the question. If the reason why we draw the positive or negative here, because if I ask you to calculate the stress at this point, for example, this point falls in a region where the normal force is positive and the bending moment is positive. So when I want to write this equation, which is n over a, when I want to write this equation now, so if the point is here, and I ask you to calculate the stress at that point, then the signs gonna be positive for the n over a, because the black part, due to the normal, is positive, and then due to the bending moment is also gonna be positive, because the moment, the effect of the moment is gonna be positive. So if the point is here, then I do have positive, positive. If the point is here, anywhere in that region, you will take the positive for the normal and the negative for the bending stress. Okay? Here is the question. Neutral axis, the location for it is gonna be like the stress is gonna be 0. And I do have two terms. And the only time that these two terms gonna be equal to 0 when they are subtracted, and that's where the neutral axis is gonna be. So the neutral axis is gonna be for a fact in that region, not down, because if neutral axis cannot be here, because you're adding the two equations together anywhere in that region, but anywhere up you're gonna subtract them, and the only way that this is gonna be equal to 0 is by subtracting them. That's why the neutral axis for a fact gonna be here in that region. And how are we going to find that? This y is always the distance from the centroid. So I don't know the location of neutral axis yet, so I'm going to set this y as an unknown in that equation. I have everything given but y. And this y is going to tell me where the neutral axis is. So I'm going to plug and chug now. I'm going to have the stress is equal to 0. I do have a normal equal to 20 kilonewton. I'll multiply by 1,000 to convert it to Newton. And I do have an area 140 times 240 millimeter. So this was plus, this equation was plus, and the other equation gonna be minus. And mx 11.6, I'll multiply by 1,000 square, because from kilonewton to Newton, that's 1,000. From meter to millimeter, that's another 1,000. That's why I multiply by 1,000 square. Y is going to be unknown. Ix, which is going to be 140, 240, cube over 12. The unknown here is y. If you plug it in your calculator, you get a y equal to 8.27 millimeter. So now I know that the neutral axis is here, somewhere above the centroid. And instead of assuming that the neutral axis was here, now this is the neutral axis. So now the centroid is that line. The centroid not going to change, because centroid is the property of area, and the neutral axis is up here. Okay? So this is the neutral axis. So from the neutral axis all the way down, it's going to be positive region. Above the neutral axis, that's plus or minus region. I haven't figured it out yet, and I'm going to figure it out using the stress equation. So which one dominate, whether the positive or negative, that's what we're going to figure it out. Okay? So next now, when you want to start calculating the stresses, I want you to name points within the cross section. And I'm going to name the furthest point, because that's where I do have the maximum stresses. I'll have A, and I'll name this B. So let's start with stress at A. So stress at A will be equal to n over A plus or minus, and then plus or minus mxy over ix. So let's figure the signs. So point A falls in a region where the negative due to the moment, that's why here is going to be negative. Okay? Here is negative. And in that, for the n over A, it's going to be positive. Okay? And now I'm going to use the same equation here, but instead of setting y as an unknown, I'm going to put y equal to 140. Because the distance, because y here is the distance from the centroid to the point where we want to calculate the stress at. So if the whole height is 240, half of it is 120. Common mistake. Don't start counting from the neutral axis. You always start counting from the centroid. Okay? So 120 here, and it's going to be equal to 8.03 megapascal. Now I want to calculate the stress at B. Now I do have normal over area, mxy over ix. And the sign here, since B in that region where both of them are positive, then I will say positive, positive. And again, I'm going to use the same equation up here. And the y also going to be 120. So I'm going to use the same equation. I'm just going to change the sign. So it's equal to, and instead of negative here, I'm going to put positive. And now I do have 9.226 megapascal. What I want to do now, I want to draw these stresses, and I'm going to extend that line. So the neutral axis is where I do have the stress is equal to 0. And I'm going to draw a vertical line because that's how the normal stress distribution change. It changes vertically. It doesn't change horizontally, because point A horizontally, so point A is the same as that point, at all points on the same line, because the equation only changes in y. It doesn't change in x. That's why I drew the vertical line. Okay? If I want to draw the normal stress distribution, 1 minute, I will draw 3 lines here and I will show you why in a moment. So this is the NSD, normal stress distribution. At point A, I do have 8.03 compression, 8.03, and then I will go down and then I'm going to close the diagram. So I have a negative here, and I do have a positive, because the lower part, which is stress at B, I do have 9.226 megapascal. And this is the final normal stress distribution in that problem. But let me break up this graph. So we solved the stresses using the equation, but let me break up that equation. So we know, for example, the bending stress only at point A, the axial stress only at point A, which is this part only, this is equal to 0.5, okay? 0.595. And the axial stress at B due to only axial force, that is 0.595, which tells you that the axial stress distribution only, both of them were positive 0.595. So I'm going to draw the stress, which is constant all the way, 0.595, which is due to the normal force only. Due to normal force, every point within the cross section feels a stress of 0.595, right? That's due to the normal stress only. That's why I told you at due to the axial force of 20 kilonewton, every point within the beam feels tension. That's why you do have, there is no variation, it's tension, tensile stress. And then bending stress distribution, which is that part, the second part here. So bending stress at point A, only bending stress, you do have negative 8.63, and at point B, you have positive 8.63. That's why if I want to draw here, negative 8.63, and then bottom 8.63. Notice that it didn't go to the 0 at the neutral axis because, again, this is not the final drawing. It is just I'm breaking up the equation. So this is the stresses due to ASD, and this is the stresses due to the bending stress only. When you add the two diagrams together, these two diagrams together, like these two diagrams together to get the normal stress distribution, you will find minus 8.63 plus 0.595, that's why you'll get negative 8.83. And when you add 8.63 plus 0.595, then you will get the 9.226. And this is your final normal stress distribution. Okay? Finally, what I want to do, I want to calculate the strain. So let me take this guy. Okay, and I'm going to extend the neutral axis line. So this part is due to normal stress. This was just, I'm breaking up the diagram, and this is the final diagram. So what I want you to draw, I want you to draw this. Okay? Second thing, I want to calculate the normal strain. So the normal strain, you can also calculate it graphically, which is getting me the strain for the ASD alone, and then a strain, like an axial strain here, and then a bending strain here, then to get me the final strain. Or you can use the diagram. Also, you can use the equation right away. So if I want to use the equation, what I want to say strain at A. But now I do have strain due to the axial force and strain due to the bending moment. So I do have two strains now. And of course at point A, the strain due to the axial force is positive, and the strain due to the bending moment is negative. A strain due to the axial force, if you remember, the strain is equal to a stress over modulus of elasticity, and that's the Hooke's law. Minus, I can also say a stress over E, also Hooke's law. But now, let me break up the equation. So the stress due to the axial load was force over area, so I want to say P or N, let me say P over area times E, right? Minus the bending stress was mx y over ix times E. Okay, so let me now just plug and chug now. What I do have, the normal force was 20 times 1,000. The area was 140 times 240 times E. I didn't write E here. Yeah, but E for wood is equal to 11 gigapascal. So let me write the E here is 11. I'll multiply by 1,000 to convert the kilonewton in gigapascal to Newton, so that now I have megapascal. So I have Newton up, Newton millimeters square, and then I have millimeters square. Minus the moment was 11.6, I'll multiply by 1,000 square. Y, and Y here is 120 because that's the distance from the centroid to point A, and then Ix, which is 140, 240 cube over 12 times E, which is 11 times 1000. What I'm going to get, I'm getting 0.00073 unitless because it's millimeter over millimeter. Now that was a stress at point A, sorry, the strain at point A, which was, it was negative, which I forgot to write, and then I will go negative here, 0.3073, and I'm gonna put negative here. Now let me calculate the strain at B, which is gonna be the same thing, but the sign is gonna be different. So let me just copy what is written here. But instead of one is being negative, both of them should be positive. Okay? And just leave everything in your calculator and just change the sign. I don't want you to plug everything again. What you're gonna get is 0.30838 and unitless, and I will go like this. And what you notice that the strain is linear, and also the stress is linear, because the strain is function of y. That's why it's linear, not y squared, it's just y, that's linear. And then the reason why stress is also linear, because stress is function is directly proportional to y, not y squared, it's just y. So it's always gonna be straight line. You're not gonna see any drops or anything. And finally, if I do have the biaxial, so where I do have two moments, it's called biaxial. If I only have one moment, it's called uniaxial. So if I have two moments, and I do have, let me put here like a normal force of, let me write it positive, for example 20, and let me change the color so that I can put the signs inside the graph. So I'm having this in green. So due to mx in green here, the upper side is in compression, the lower side is in tension. If I do have a bending moment my in blue here, so due to the bending my, both sides in compression, this side is in tension. And due to the normal force, which is in black, I do have plus, 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 plus. Everything is positive due to here. So here is the thing, where the neutral axis is gonna be. So remember, the neutral axis is gonna pass through the quadrants where you have different signs. So the neutral axis will never gonna be in this quadrant, because you're gonna add all three equations together, all these three terms together. So for sure I know the neutral axis is gonna pass through this quadrant, and that quadrant as well. So what I'm expecting the neutral axis is gonna be somewhere like this, where it's gonna pass through all three quadrants. Okay? This is somehow advanced. I just put it there just also to show you how this sign method will be easy for you to determine the neutral axis. Okay? That's all I have, and I'll see you next time.